Hello everyone, welcome to iitiansgateclasses. So in the last session we have seen your questions of time response as well as the theory of your time response. So in today's session we are going to see what? We are going to see your Routh-Hurwitz criterion. Okay, so then let us begin with today's session. So Routh stability criteria. So up till now we have seen what? We have seen the basics of control. We have seen how to represent your transfer function with the help of block diagram as well as your signal flow graph. Then we saw the time domain parameters, your steady state time means steady state responses and your transient response we have seen. Now basically we are interested in determining the stability. So stability can be defined in terms of two parameters. One is absolute stability, other is relative stability. So absolute stability basically defines your stability in terms of pole location. Okay. So if poles are located at the left hand side of S-plane, then system is going to be stable. If it lies on your imaginary axis, so that will be marginal stable. If poles lie on the right hand side, then system will be unstable. And relative stability, it defines your stability in terms of zeta, gain margin and phase margin. So at the moment I am not going to define your zeta means gain margin and phase margin. Okay, so we will see that in your next chapter that what is gain margin and phase margin. Okay, so I told what, if your pole, if this is your S plane, okay, if this is sigma, this is j omega, and if this is your S plane, then if your poles lie in the left hand side of S plane, that is in this region, so this will be what? This will be your stable system. If poles lie on the j omega axis, then your system will be marginal stable, and if your poles lie on the right hand side of S plane, then it will be unstable system. Okay, it will be unstable system. Okay, so now let us study how to calculate or how to know the stability with the help of Routh stability criterion. So Routh stability criterion is going to define us the absolute stability. That means what? That the stability is going to be defined on the basis of your location of poles. Okay, so now let us see what? Let us see your properties of Routh stability criterion. So it is used to determine stability of any polynomial. So like this method, it was developed in your mathematics. Okay, so in mathematics, Routh condition was used to determine whether your poles, complex poles, will it lie on your left hand side or right hand side of your complex plane. So this has been actually incorporated in your control system. So for the closed loop system to be stable, first column of Routh-Hurwitz table should be of same sign. Okay, so we are going to discuss this, but over here I have written all the points. So we will see one by one what all this point mean. Okay, so for closed loop to be stable, first column of Routh-Hurwitz table should be of same sign. So next is what? Number of sign changes in the first column represents number of right hand poles. Okay, so whatever will be the number of sign changes in the first column of your Routh table, that will represent basically what? It will represent the number of right hand poles. If any power of S is missing, then that represents a presence of pole in the right hand part of S plane. So one by one I am going to discuss all these points. Okay. If the characteristics equation consists of only even power of S, then that represents presence of pole on your imaginary axis. And last point is what? If imaginary axis contains repeated pole, the system will be unstable. So let us start from the last point. So I have written what? If imaginary axis has repeated poles, so let us assume this is sigma, this is j omega, and if a system has repeated poles on your imaginary axis, that means what? There is two pairs of pole located at plus minus 1 j1. Okay. So now if I want to write Ts over here, so that will be what? 1 by S square plus 1, okay, whole square. So we know what? So we know what? That this will be actually equal to, if I want to take inverse Laplace, so sine t, okay, sine t has Laplace transform 1 by S square plus 1. T sine t will have Laplace transform minus d by ds xs, or if you differentiate this, this will be S square plus 1 whole square minus 2s. Okay, now this s, okay, this s we have over here. So what can we do to remove this s? Basically, if we integrate this, okay, if we integrate this from 0 to infinite, what will happen? That will be xs by s. So this s will cancel. Okay, so over here we have plus because there is minus. So basically t sine t, when we integrate, so t sine t, or it looks something like this. Already I have told you control system is your causal system. So means all the transfer function are causal over here. So that is why I have taken the limit of integration from 0 to infinite. So now this will look something like this graph t sine t. And if you see one thing, that if you integrate this, okay, if you integrate this, this will be equal to infinite. Why? Because whatever is the area above this sigma axis, okay, oh sorry, this is your time axis now because this is t sine t. So whatever is the area above this axis, there is a difference in your area. So this will not be a finite number, this will go to infinite. Okay, so over here you can see, if your impulse response has area infinite, so that means what? That is your unstable system. So imaginary axis contains repeated pole, then system will become unstable. So next what we have written, if the characteristics equation consists only even power of s, then that represent presence of pole on imaginary axis. So if suppose we have your characteristics equation that looks like this, s square plus 1 equal to 0. So you can see s will be equal to plus minus j. Next, if we have characteristics equation like this, s to the power 4 plus 3 plus 4s square plus 3 equal to 0. So over here you can substitute s square is equal to x. So this will be x square plus 4x plus 3 equal to 0. So s is equal to minus 3 minus 1. So sorry, x is equal to minus 3 minus 1. So that means x is equal to s square. So s will be equal to plus minus j root 3 plus minus j. Okay, because minus 1 under root, it will be plus minus j. So you can see the poles are always lying on your imaginary axis. So even power of s, if your characteristics equation contains only even power of s, then that will represent that poles are on imaginary axis. If any power of s is missing, then that represents a presence of pole in the right hand part of s plane. So for this, if we have something like this, s square means I cannot, okay, so s square plus s to the power 1 is equal to 0. So if this is your characteristics equation, so here you can see if you take s common, so this is becoming s plus 1 is equal to 0. So you might argue that, sir, where you are getting your means a pole on the right hand side of s plane. But what I told you over here that any one of the coefficient, any power of s should be missing. Okay. So that means what? Over here s to the power 0, if it is missing, then it's okay. But if your characteristics equation, it looks like this: s cube plus 3s square plus 1 equal to 0. If you solve this equation, so you will get one negative root, or sorry, you will get one positive root, and positive root will imply that there is actually a pole in the right hand part of s plane. So you can solve this equation in your calculator or even in your Rao-Hurwitz table. Later on we will solve this and we will check that whether there is a right hand pole or not. Okay. So next, number of sign change. So this we are going to see in your Raoult table. Okay. So now let us see how to formulate the Raoult table very quickly. So if suppose our characteristics equation, so characteristics equation is what? 1 plus GHS equal to 0. So if our characteristics equation, it looks something like this: a to the power 4 s to the power 4 a3 s cube plus a2 s square plus a1 s1 plus a0 is equal to 0. Then how do we formulate the Raoult table? So it is very simple. So s to the power 4 s cube s square s to the power 1, or let me keep spaces over here, s square s to the power 1 s to the power 0. So first we make a table like this, and then in s to the power 4 we fill all the coefficient of the even power. Okay. So that will be what? So a4, a2, a0, and in s cube we fill the entire row with all the odd power of s. So that will be a3, a1, and there is no more over here, so we will put a blank. So this blank corresponds to 0. Now how do we fill the subsequent rows? So look over here, for filling this element, basically we will cross multiply this and subtract. So a3 dot a2 minus a4 dot a1 divided by a3. So this is your first element of this third row. Next, if I want to do, so again cross multiply this with this and this over here, and then you need to subtract. So that will be a3 dot a0 minus, so this is 0, so 0 into anything will be 0, divided by a3. So a3 cancel, only thing remaining over here will be a0. So this is a0 and next will be blank. So if I want to write s1, so let us assume this is b. Okay, this is b. So over here this will be what? B dot a1 minus a0 dot a3 divided by b, and this will be blank over here because b into blank and this also into blank, so this will be 0. Now last element will be what? If this is your c, then last will be what? C dot a0 divided by c. So this will be what? This will be a0. So like this we fill what? We fill your Raoult table. Now for your Raoult table to be stable, so let me write it like this once more. So over here I will rewrite the table once again. So this is a4, a2, a0, a3, a1, blank. and over here we have B A naught blank, over here we have C blank blank, and last we have A naught. So for your route table to be stable, all the element of your first column, it should have same sign. Either it should be positive or it should be negative. So if this is the case, then all the poles of this characteristics equation, or the roots of this characteristics equation, all the roots will lie in your right hand part of S-plane. But if suppose there are sign changes, okay, so let us assume that over here we have negative sign, over here we have negative sign, and over here there is positive sign. So now in this case, this is your what? This is your fourth order characteristics equation. That means there are 4 roots, or there will be 4 poles. So now out of those 4 poles, if you want to see how many poles are in the right hand part of S-plane and how many poles are in the left hand part of S-plane, so you need to calculate it. So look over here, sign change. So this is plus plus, no sign change. From plus to minus there is 1 sign change, then again from minus to minus, and then again from minus to plus. So there are in total 2 sign changes. So number of sign change actually indicates your number of right hand poles. So in that case it will be 2. So this is how we make conclusion about your route table and the number of poles that are present in the right hand part of S-plane. So now let us see few examples. So I have taken 3 examples over here. So let us try to solve them one by one. So the first example that we have is S cube plus 5s square plus 6s plus 20 equal to 0. Okay. So this is the first example we have. So let us construct the route table very quickly. S cube, S square, S to the power 1, S to the power 0. So this will be odd powers of S will be filled over here. So 1, 6, and this will be blank, and next will be 5, 20, and this is blank. So this is 6 5s are 30, 30 minus 20, that is 10. So 10 divided by 5, so that will be 2. Remaining all will be blank, because 5 into blank and blank into 1, so that everything will be 0. So in the next your row you are going to write 20 into 2 minus 5 into 0, so that will be 0 divided by 2. So over here we have 20. So now see in the first column. So is there any sign changes in the first column? So you can see there is no sign change. So number of sign changes actually indicates what? It indicates your number of right hand pole. So that is equal to what? That is equal to 0. Okay. So number of sign changes is equal to number of right hand pole. It is equal to 0. So this system is stable. Okay. Stable system. Okay. So now let us see the second example. So second example is what? S cube plus 5s square plus 6s plus 35. So if we solve this, so once again let us make the route table. So if you fill the table over here, so that will be 1, 6 blank, and this will be 5, 35 blank. So over here if we start filling, so 6 5s are 30, 30 minus 35, so that will be minus 5 divided by 5, so minus 1, remaining all will be blank, and this will be what? Minus 1 into 35 minus 0 divided by minus 1, so that will be 35. So number of sign changes, you can see one of the sign changes is over here from plus to minus. Another sign change is from -2 plus. So the number of sign changes, it is equal to how many? It is equal to 2. So number of right hand poles are how many? Number of right hand pole is equal to 2. So over here we have 3 poles. So out of those 3 poles, 2 are in the right side, 1 is on the left side. Okay. So in the next example, example number 3. So our characteristics equation, it looks like this. So s cube plus 5s square plus 6s plus 30. So let us construct the route table. So this will be s cube, s square, s to the power 1, s to the power 0. So this will be 1, 6 blank, and this will be 5, 30 and blank. Okay. So this is 6 5s are 30 and 30 minus 30 0. So remaining all the means this all the entries of this third row, it will be what? 0 only. So you can see this is one of the special case of route table when we have an entire row 0 and this is known as row of 0 or ROZ, row of 0. Now row of 0 basically indicates that your poles are symmetrical about origin. And now how do we actually then fill, means how do we make your calculation about the stability? So it is very simple. We take into consideration the auxiliary equation. Okay. So auxiliary equation is just the above coefficient of S where your row of 0 has occurred. So above this we have this row. So fill the coefficient of this row. So this is even power of S. So that will be 5s square plus 30 s to the power 0 equal to 0. So this will be s square plus 6 equal to 0. Okay. So this is your auxiliary equation. Okay. This is your auxiliary equation. So now we basically differentiate this auxiliary equation with respect to S. So this will be 2s plus 0, and this is actually the coefficient of this auxiliary equation we are going to fill over here in the row of 0. So this is 2s to the power 1. So over here we are going to fill 2 and remaining all the coefficients are 0. So this will be 0. So now we can do what? We can fill the route table. So this will be 2 into 30 minus 0 divided by 2. So this will be 30. So over here you can see there is no sign change. So that is why your system is stable. So this is stable system. Now basically the roots of auxiliary equation is actually what? It is your root or poles of your characteristics equation. So what is the root of this auxiliary equation? S square plus 6 equal to 0. So S is equal to plus minus j root 6. So this is what? This is your basically what? This is your root of this. So if one of the root means two of the roots are like this, so I can even get the third root. How? By dividing. So s square plus 6, if you divide this characteristics equation by s square plus 6, you will get the other pole also. So this will be s cube plus 6s. Okay. So this will be minus, cancel. So this will be 5s plus 30. So if you write 5 over here, so this will be 5s square plus 30. So this will cancel out. So the third root is s plus 5. So you can note one point over here that whenever we have your row of 0, we can entirely find the location of poles also. Okay, you can see we have found out the location of poles also. Over here you can also find the location of pole, but here it is simple because this is your third order system, so you can use your calculator. But what if it is your fifth order, sixth order system? Then you cannot find the location of pole. But even in those cases we can find it actually if there is row of 0. So over here you can see row of 0 is indicating that your system is marginal stable also. Okay, it is indicating that your system is marginal stable, but don't make a conclusion that whenever we get row of 0 that means your system will be marginal stable, because just in a moment I am going to show you other possibilities of pole 0 plot when you have row of 0. Okay, so you can see what are the properties of row of 0. So whenever an entire row becomes 0, so this always happens in the even power of s. Okay, ROZ always happens in your even power of s. You can note in the last question also. So ROZ, in the odd power of s. Auxiliary equation always we have what? Even power of s. Okay. So whenever an entire row becomes 0 in the odd power of s, then we form auxiliary equation, and the differential coefficient of auxiliary equation replaces the row of 0. Row of 0 occurs only when poles are symmetrical to origin. Auxiliary equation, just now I have told you, consists of even power of s. Roots of auxiliary equation is the roots of characteristics equation I have discussed. If more than one ROZ occurs, that represent presence of repeated poles. Okay, repeated poles. Now let us see how your poles can look when you have ROZ. So if suppose this is your S plane, so one of the combination of ROZ, it can be so one of the combination, it can be like this. Okay, when we have what? When we have your third order system, so we can have ROZ. So over here we have a single ROZ. Okay, single ROZ, ROZ is equal to 1. Now over here we can also have poles like this. Over here also number of ROZ is equal to 1. Okay, number of ROZ is equal to 1, but over here your auxiliary equation, it might look like this: s to the power 4 plus 4s square plus 3. Okay, so at that time you will have what? Multiple poles at different location on the j omega axis. Now your ROZ can be also like this. Okay, so if suppose there are repeated poles like j1 and j1 minus j1 minus j1, so here your number of ROZ will be equal to 2. Okay, so note over here that the number of repeated poles you have, that actually implies what? The number of ROZ that you will be having. Now I told you what? That sometimes ROZ, you can see most of the cases here ROZ is implying that your system is marginal stable. But sometimes your pole zero plot, it might look like this also. So over here ROZ is also 1, and you can see this is symmetrical about origin. So your ROZ can be like this. Now one more case, it can be like this. Okay, so this is also symmetrical to origin, and this is unstable, this is not marginal stable. And one more condition, you can have something like this also. So this is also what? This is also unstable system. So for all the cases you will be having ROZ. So over here also ROZ is equal to 1, here also ROZ equal to 1. Okay, so you can see what? That repeated ROZ actually implies that there are repeated poles. Okay, okay, fine. So now let us check one of the special cases of Routh-Hurwitz table. So let us solve this very quickly. So if you make the route table over here, so this will be s to the power 4, s cube, s square, s to the power 1, s to the power 0. So now if you fill over here, so this will be what? 1, 2, means even power of s you need to fill. So 1, 2, 8, and next you can see 2, 4 and 0, 2, 4, 0, or even blank you can write. So now if you solve this, so 2 into 2 is 4, 4 minus 4 is 0. Okay. So the next if you see, so that is 2 into 8, 16 minus 0 divided by 2. So over here we get 8. So this is not actually row of 0. Why? I have already told you ROZ, in that we have an entire row 0, but here you can see only the first element is 0. Now this is problematic. Why? Because if you come over here in the next row, this will create infinite because you will be dividing by this element. So how do we proceed then? Then we consider one element epsilon over here. So now we solve this. So this will be 4 epsilon minus 16 by epsilon, where your actually epsilon tends to 0. And next all the terms will be 0. And over here you have 4 epsilon minus 16 by epsilon into 8 divided by this element. So this will be 8. So now if you solve this, 4 epsilon minus 16 by epsilon. So you can do what? Here you can see this is infinite. So simply divide by epsilon in the numerator and denominator. So this will be 4 minus 16 by epsilon. So if you put 0 over here, you are getting minus infinite. So over here you will be having minus infinite. So the number of sign changes, you can see this is 0. So from here positive sign to negative sign, one sign change, and from minus negative to means minus to plus, once again you have one more sign changes. So the number of sign change is equal to what? It is equal to 2. So this implies number of right hand pole is equal to 2. Sometimes they even ask in question like this, number of left hand poles. So number of left hand poles will be how many? Number of left hand pole is equal to total number of poles. So this is a fourth order equation. So there will be 4 poles in total. Out of that, the number of poles that are in the right part, so 4 minus 2, that is 2. So check the question. If they have asked whether the roots, they are asking about the roots that are located in the right side, or if they are asking about the roots that are located in the left side. So be very cautious, look at the question and then solve it. Okay. So now next we have few objective type questions. So I will give you 1 minute to solve each of the questions. So this is the first question. Please solve it quickly. So you can see over here that a system is described by the transfer function. This is stable, the constraint on alpha and kr. So they have told you that this is the transfer function. Now don't do 1 plus hs equal to 0. Don't do it like this, because they are asking about your constraint of this system only. Okay. So for this, your characteristics equation is what? It is s cube plus alpha s square plus ks plus 3. So very quickly make your route table. So that will be s cube, s square s to the power 1, s to the power 0. So this will be fill all the odd powers, so that will be 1k blank, and this will be alpha 3 blank. So this will be what? Alpha k minus 3 by alpha, and all the remaining will be blank, and over here this will be what? So 3. So now for this system to be stable, you can see this is positive, this is positive. That means alpha should be greater than 0 first, and alpha k minus 3 by alpha should be greater than 0. So that means alpha k minus 3 greater than 0, or alpha k is greater than 3. Equation 2. So which option do you see? Alpha k is greater than 3 only in this option present. So option B is your correct answer. So we have this next question. Very quickly solve this. So you can see if we fill the route table over here, so that will be what? 119 blank, and this will be 812 blank. Okay. So now if you start filling over here, so this will be what? 8 into 19 minus 12 by 8, this will be blank. Next will be what? Whatever is this value divided by this value, so this will be what? 12. So 19 into 8 minus 12 by 8. So obviously this is going to be your positive number, even if you don't know how to solve. So it's okay. It is totally okay. You don't need to solve this. So you can see over here that basically this will be your stable system. So option A is your correct. So next question, how many roots of the following equation lie in the right half of S plane? So very quickly solve this. So over here, if you start filling, so this will be 2, 2, 2, 10, and this will be 1, 5 blank. So this will be 2 minus 10 by 1, so that is minus 8, and this will be 1 into 10 divided by 1, so that is 10. So next will be minus 40 minus 10, so minus 50 by minus 8, so that is 50 by 8, and this all will be blank, and the last term will be 50 by 8 divided by 50 into 10 divided by 50 by 8, so that is 10. So the number of sign changes over here, you can see what? Number of sign changes is equal to 2. So this is actually the number of right hand poles. Okay, so these are the number of right hand poles. So how many roots of the following equation lie in the right half of S plane? So that is 2. Option B is your correct answer. So in the next question we have what? So quickly solve this question. So I am giving you 1 minute. So you can see the first element of each of the row of a Routh-Hurwitz stability test showed the sign as follow. So this is the first element of each row. So consider the following statement. So over here you can see this is what, that there are basically 1, 2, 3, 4 and 5 rows over here. Out of that, this is plus, plus, minus, plus, minus. So you can see over here the number of sign changes are how many? So number of sign change is equal to 2. So can you tell me what is the order of the system? Order of the system over here means what is the highest power of the characteristics equation? So if this is s to the power 0, s to the power 1, s to the power 2, s to the power 3, this is s to the power 4. So highest power of s is s to the power 4. So there will be 4 poles over here. Out of those 4 poles, 2 are in your right hand part. So let us look at the statement. The statement first over here is the system has 3 roots in the right half of S plane. So this is wrong. So one sign change, and over here, sorry. So we have one sign change over here, second sign change over here, and third sign change over here. So the number of sign changes are 3. I am very sorry. So there are 3 sign changes. So this is correct. The system has 3 roots in the left half. No. The system is stable. No. The system is unstable. So 1 and 4 is correct. So option B is your correct. There are 3 poles in the right hand part of S plane and 1 pole at your left hand part of the S plane. So the next question we have is this. So quickly solve this. So you can see over here the characteristics equation of a control system is given by this. What is the value of K for which this system is marginal stable? So quickly fill the Routh table. So over here this will be 1 4 K and this will be 4 3 blank. So this will be 16 minus 3. So you need to find the value of K for marginal stable. So 16 minus 3, that is your 13 by 4. And this will be K blank. So over here this will be what, 13 by 4 into 3 minus 4K divided by 13 by 4, and remaining all will be blank, and this is K. So now for your system to be marginal stable, there should be row of 0. I have told you row of 0 happens only in your odd power of S. So this is one odd power of S, this is one more odd power of S. But over here you have your row fixed for S cube, but here it is not fixed. So what I will do, I will equate this to 0. So 13 by 4 into 3 minus 4K by 13 by 4 equal to 0. So this will be equal to 0, or this is equal to what, 4K is equal to 13 into 3 by 4, or this is equal to K equal to 39 by 16. So option D is your correct answer. So for K equal to 39 by 16, you will be having what? You will be having the system in your marginal stable. So this was all the concept about your Routh-Hurwitz criteria.